Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do on coupled temperature displacement analysis. So it's heat transfer combined with the structural stress, because there is a heat transfer, so there is a thermal gradient. So if there is a thermal gradient, then there is a, because of thermal gradient there is a thermal expansion, and because of thermal expansion you have thermal stress generated because of this heat transfer and thermal gradient. So there are a lot of places where you want to do this coupled temperature displacement analysis. So heat transfer combined with structural engine, there are like a sudden cooling, thermal shocks are there. Like engine part, you say if engine doesn't dissipate heat quickly, then there is a gradient generated within the engine cylinder, and that required a thermal robustness capability for engine. Something like roof application, where actually you required not heat immediately transferred to the bottom, and so you want the insulation property. So there are a lot of application where you want to combine heat transfer with the structural engineering. So one of that problem we have just taken a specimen, a cast iron specimen. We have keep this inside a oven, and the oven temperature is 600, and we just try to do the thermal robustness. So right now on my screen what you see is how the part is get displaced. Then I'll just quickly show you. I just given a quite a bit a uniform displacement, so I'll put 25. So you have radial and then axial displacement of workpiece, and then we'll also look some of the field parameter. We'll also see how the temperature is distributed. So this is inside the oven. So from outside the heat is getting to the workpiece surface, and then heat is getting transferred inside the core. But then still you see the core is not that hot, similar like outer periphery. So this is exactly problem we'll see. And because of thermal expansion you get axial stress. For this particular case it will be axial stress generated, and this axial stress is because of thermal expansion. So we'll also have a look into axial stress. So you see, because it's moving out, axial and radial, the core is getting tensile stress, and this is in Pascal. You may be surprised why this high number. It is a Pascal. We are going to use kg, Newton, meter. So we'll go to the problem now. Now this is very interesting and important topic, where you want to combine thermal engineering with the structural part. So coupled temperature displacement analysis in Abaqus. Now before going to touch this topic, coupled temperature displacement analysis in Abaqus, we need to understand some of these terms. There are a lot of terms in this heat transfer, but the names looks fancy: thermal diffusivity, thermal conductivity, specific heat. But if you understand properly, it is not a rocket science, and these terms is very important. Abaqus is very robust in terms of heat transfer, but we need to understand these terms very well. So once we understand these terms, you can solve any problem. So let's understand the first thermal diffusivity. Thermal diffusivity is also called as a thermal robustness of the part. So if your part should be a very thermal robust, so it there should not be very high thermal stresses generated, then it should transfer heat immediately. So if you have a high conductivity, low density and low specific heat, then people say you have a high thermal diffusivity. So if you have high thermal diffusivity, the thermal stresses generated are quite lower, and thermal diffusivity is high in terms of metal. So if I give a heat and I start boiling a water, and if I put two spoons, one is a metal spoon, one is a wooden spoon. Since so metal spoon, your density is high, your conductivity is high, and then your specific heat is also quite high compared to the wooden spoon. So heat will immediately transfer in a metal spoon. In case of wooden spoon, your conductivity is low, density is low, specific heat is there, so heat will not immediately transfer from the boiling water to your hand. So now this is give a quite clarity what is thermal. Thermal diffusivity gives you how quickly you can transfer the heat within the part. So it's very important property, thermal diffusivity, when you design a part, something like um, a car engine or two-wheeler engine. You want the heat should dissipate fast, because if heat doesn't dissipate fast, then engine temperature, cylinder temperature go up, and then engine then susceptible for a cracking or failure. Now we'll quickly have looked into what is thermal conductivity. So high thermal conductivity is like aluminum. So within the part, heat will transfer because of thermal conductivity. So if you have low thermal conductivity, then the heat will not transfer very fast. Now we'll also see the problem. What we are going to do is we'll have a similar cylinder. We'll have some initial temperature. We'll give energy pulse to this, and we'll give this H, heat transfer coefficient, to the part, and then we'll see how it is going to dissipate. So thermal diffusivity is the how fast you can the heat propagate within the part, and which is the combination of your thermal conductivity, density, and specificity. Some people might say, okay, my thermal conductivity is high, but same time you have high density and high specificity, then your thermal diffusivity may be in same range. But if you have low density, low specificity, high thermal conductivity, it will quickly dissipate the heat. Now specific heat. So this is very important term, specific heat, and then a lot of people get confused because of specific. Specific heat is nothing but, if you understand this equation, heat, so mass into specific heat into temperature. So if you want to raise a temperature of say 1 degree of 1 kg mass, then whatever heat is required to raise that temperature by 1 degree, that is called a specific heat. So in terms of water specific heat is very high. So it is 4200 joules. So the heat required for 1 kg of water to raise its temperature by 1 degree, you require quite a bit heat. Here. But something like oil, it's have low specific heat, so you require half of the heat to raise the temperature of oil by 1 degree. And something like concrete, which is quite like 850, you required a much lower heat to raise that concrete temperature by 1 degree Celsius. So this is the term. So a lot of people get fancy about this, but specific heat is if you have 1 kg of mass and you want to raise that temperature by 1 degree, so how much joules of energy you require, that is called as a specific heat. So it's like a joule per kg Kelvin. So that is what you required. So for water it is a 4200. Now why you want to do combine of heat transfer and then structural engineering? Why you want to do it? Now there are a lot of problems where you want to do it. Like take an example, when you want to design or model cooking pan handle, so you don't want heat dissipate fast within this, so you want a low thermal diffusivity here, but still there is a quite a bit temperature gradient. You want to know whether handle will take that thermal shock or not. Something like an engine, two-wheeler engine, you see a lot of fins because you want to get heat out. So once heat is getting out, the temperature doesn't rise within the engine cylinder, and then it doesn't because with the high temperature your metal property degrade and you may get a thermal shock, a cracking. So you require high dissipation of it. In case of a house, you want a quite insulation, so you want a low thermal diffusivity in this. Now there are a lot of instruments available which measure this thermal diffusivity. They keep this sample inside, they give a quick heat, and they measure how the heat is going to move out. So similar type of test we are going to do. This is called a flash equipment. So what we are going to do, what we are doing is we are taking a 0.2 meter by 0.6 millimeter diameter mainly cast iron workpiece, and we are going to check the thermal robustness of this. So we'll keep this inside oven sink temperature will be at 600 degrees C, and then we'll give heat transfer coefficient H, because there will be from the because it's a warm air and with natural convection it is getting on the workpiece. So we will have outer surface and the top surface we have heat transfer coefficient, which heat will start propagating. The outer surface will get heated, and then it start getting inside the core to get heat. Now the unit which we are going to use is a kg meter Newton degree centigrade and second. Now there is quite a bit straightforward conversion degree Celsius to Kelvin, so it is straightforward one-on-one, not an issue. So we are not putting radiation right now, because then we want to do a separate radiation part and then get introduce here. So we'll put this temperature, and 7800 kg per meter will be the density. Cast iron modulus is lower, it will be like a 170 GPa. We are going to use as a Pascal, Newton per meter square will be Pascal. Thermal expansion will be 1.04 e power 0.05 meters per meter degree Celsius at room temperature. Now you can have temperature dependent metal property here, but I don't have. But in case you have, you can feed for your problem this. And then specific heat for cast iron is 460 joules per kg Kelvin. And what we are going to do, we are going to use this H, convection heat transfer coefficient. Like this H film coefficient will be depend on the surface temperature. If your surface temperature is high, it will the heat transfer coefficient will be on higher side. So if you have hot surface, then air comes with this contact with this surface, it get hot, and then it because its density once it's become hot, its density become lighter, it move up. So you get a quite natural high heat transfer coefficient with a higher temperature. So that's what actually you see. The film coefficient is lower at a room temperature, but at its move high, then it's become very on the higher side. This is actually 45. There is a typo. Then on this curved surface, will be better than at the top surface. So you have two different film coefficient. You are going to give sink temperature 600 degrees C, and then you are going to heat this piece for 2 hours. So this is exactly where go. So let's start doing the problem. So let me clear this. So let me set the directory. I'll just create thermal robustness. We'll create a now one important thing I just missed to tell you. We'll take advantage of symmetry. So we'll just model a quarter, and with quarter symmetry you can get advantage to your boundary condition and stabilize the part. So we'll create workpiece, I'll say 3D deformable solid. We are going to do extrusion. Size we are going to keep 0.05. So like first we'll make a radius. So I'll put 0,0, then 0.1, and then 0,0.1. So we'll get a 3 point, and I can put an arc. So I'll say center 1 and second, and then I'll just join these parts. Done this, we'll move this by 0.3. So we got a part ready. We'll create a metal property. Now this will be cast iron. So we'll put density 7800, then we'll put modulus 170 e power -9. 0.25 will be Poisson's ratio. If you have plasticity data, go ahead and add the plasticity data. You can also put a temperature data. Now we don't have temperature data, but you can add temperature data also, because your modulus will be different on different temperature. We'll put thermal expansion, because we are going to give expansion to this part. So our thermal expansion is 10.4 e power 06 -06. So a lot of people make this error. So it's e power -06 at room temperature. I'll put conductivity This will be again at room temperature. The conductivity will be 54, and then I'll put a specific heat at room temperature. The specific heat will be 460 at room temperature. Just want to check one more time whether I put the right property there. So it's quite perfect property we have put. Now we'll create solid. It will be homogeneous. I'll just quickly assign that. So we assign that. Now we create a property. We'll go to assembly, and then we'll create workpiece assembly. So we've done that. Now I will go to the step, and then we'll create thermal robustness test. Thermal and then we'll select coupled temperature displacement. So you give a name, select coupled temperature displacement. So given this NL jump on, this will be non-linear property on, because you see, because of temperature variation you may get a large displacement. We have quite a bit symmetric part. We don't want to get into automatic stabilization. You can include creep effect also, viscosity effect if you want. And then the time period will be 2 hours, so 7200 seconds will be the time period. So we are going to start with initial 1, and I'll say 1000, and will not allow to go to temperature more than 25. So this is how we have created. You have selected coupled temperature, you are given actual time, you put NL jump on. Initially you started with 1 second, and then maximum is 7200 seconds. Now what we are going to do, on outer surface you have a film coefficient H. So your convection heat transfer is HA delta T. So the if you put a fan, you blow the air, your H will be high. If it is a natural convection, it will be lower side. But if you have as temperature goes up, because of density difference, you get a quite a high H in natural convection also. So we'll first interaction property manager will create film condition. So I am saying outer and temperature dependent. So my condition on the outer side, I am saying it's a coefficient is 15 at the room temperature, then 25 at 200, then 35 at 400, and 40 at 600 degrees C. Then this will be enough. I'll create one more on the top, because top surface is not that easily accessible because at the top, so you'll have lower side. And this will be just to show you how you can even change the film property and see how that influence your heat transfer within the part. So you define a H. Now what we'll do, now we want outer surface and then top surface. So we'll create surface film condition. So it will be outer. I'll select outer, done. Now this is important step. So you say outer, and then you want film coefficient. So you say property reference and you say outer. So whatever the temperature dependent film coefficient, it will access here. Sync temperature, you are saying uniform, it will be 600 degrees C. Is it instant or you want to apply it as amplitude? So we are going to create an amplitude. We are saying at time is equal to 0, it is everything is at 23, and then 7200 you start giving this heat 600 degrees C, and then you connect that. So this is what we have done on the top side. We'll create also outer, we'll create also for top. So surface conditioning, and then you select the top, and then you say property, you select the top, uniform, and then you say 600, and then amplitude. Okay, so you created both interaction properties, and then create. Now we'll create a couple of load cases, but first we'll finish the meshing also part, so that way it will be easier for having loads. Structural side, you'll put X symmetry, sorry, we'll have the boundary condition, so it will be X symmetry. So let me select the X symmetry. So this is the X symmetry here. So this is X symmetry. We'll also create Y symmetry. We'll also create a Z symmetry in the center. So given a structural boundary condition, now we want to have this workpiece at initial room temperature 23 degrees Celsius. So first we'll just quickly do a mesh, and then we'll give that initial, or you want, you can give it here also, predefine other. So initial 23, and then you can select everything and then give 23. So again the initial boundary condition also. We'll quickly do a meshing. Now this is also important step. You need to select element which will have couple temperature displacement. So you have to select in part. So you go and select this, and then standard linear, but then you choose couple temperature displacement. So you have 3D, you select couple temperature, so it is like a C3D8T, and that's what actually it is assigned. I select for this type of component sweep and middle axis, and then we are going to give 0.005, so that way you can get fine meshing also. So you get a quite a good structural mesh also. Now what we have done a part, we are given a thermal and structural both property. Thermal property we are given like a conductivity we are given, specific heat we are given, expansion is structural property, then you given elasticity, you can have plasticity, and you are given density. So how the heat is going, thermal diffusivity, it can calculate from conductivity, displacement, and the specific heat. And because of temperature gradient, what is the thermal expansion, it will calculate from this thermal expansion, and from this thermal displacement with the modulus given, it will calculate what is the thermal stress. So this is what is the exactly game. So conductivity, density, specific heat, it will calculate what is the thermal diffusivity. Based on the gradient, it will call what is the thermal expansion. With this thermal expansion in the metal property, it will calculate what is the thermal stress within the part. Now we'll create this thermal robustness. So we'll quickly do a data check. So we're gonna for a data check, and I always recommend you should go do a data check. So once you do data check, at least you get a better idea how so pre-processor done, and then successfully completed. So I think pre-process everything, data check is done. Let's submit it, and once it's submitted, we'll just quickly have a we'll just look how is the input file looks like. So you have node define C3D8T is couple structural temperature displacement element. Then you have part definition, assembly definition. You have this element set, node set, you created surface. Now you given material properties. Then this is are the film property. So with the temperature, the convection heat transfer coefficient is also changing for two different surface. You given structural boundary condition, X symmetry, Y symmetry, Z symmetry. You given all initial temperature, room temperature. You are seeing from 1 second to 7200 second. The sink temperature you are given as 600 degrees C. Outer you are also created the amplitude. Amplitude is like for 0 time 23 and at this 600. So this continuous heat sink temperature is going on. Now we have submitted. Just quickly look how the results look like, if there is anything. Let's check what is so just first is got unconverged. So just wait for results to get out, and then we can discuss on this part. So guys, just check a monitor. It gone to 5 seconds. Just quickly check the results. How is the heat is getting translated. So its heat just started dissipating from outside to inside. So you can see it is just moving from outside surface to inside, and then slowly core will get heat, but then you'll have this temperature gradient. So I'll also have a look how axial stress, because axial stress is going to generate the thermal shock, and it is going to give structural failure to this spot. So your axial is also start generating because of this gradient. So it will just keep on going. So it take a long time to solve this type of problem. So I'm not going to wait till it get finished, but you can look into your results and do on yourself. The most important learning out of this is how you can do coupled temperature displacement analysis, which was pending from our side long time. So I guess this will be useful for you to do your projects or actual real-time simulation. So go ahead and have a happy learning. If you like this video, don't forget to like us and subscribe us. Thank you. Bye bye.